All right, so this is going to be problem number 2 from the class packet for chapter 7, where we're working on rotational motion. Okay, a 250 kilogram motorcycle is driven around a 12 meter tall vertical circular track. So we're going to use that as, that's going to be the radius, which is going to be 6.0 meters. I will note here that we'll be assuming that has 6.0 meters instead of 6, just because I want to have 2 sig figs in my answers. I'm kind of fudging the rules here a little bit, but let's just roll with it. It is being driven at a constant speed of 11 meters per second. Okay, so that's the 11 meters per second. It is customary to just use v here instead of v sub t. Technically, it is v sub t. This is a tangential velocity, so it is working, tangent to that circle. Okay, determine the normal and the friction force at all of these various locations around the circle. Okay, assume that the mass of the motorcycle includes the mass of the rider, and aerodynamic drag and rolling resistance are negligible. So we never talk about aerodynamic drag. That's just referring to the air resistance, and then rolling resistance is not something we've talked about at all. So don't even worry about that at the moment. Okay, so we've got 4 locations, 1, 2, 3, and 4. And then I've got an extension for number 5. I'll have to do that live because I want to get on Desmos to show you how to do it. But these are the locations, okay? So let's see. So here's our little circle right here. Oh, I did not mean to move the circle itself. And we've got these 4 locations, and I'll draw some dots, to show you where we're looking at, okay? So the first one is at the bottom and rising. The second one is halfway up. The third one is at the very top. And then the last one is 40 degrees past the top, okay? So if you haven't figured it out, obviously the last one is the hardest one. And is the one you want to focus your energy on, because you can do that. You should be able to do the others. Now some of you will just go, I don't want to, but I mean, you got to get the last one. And the last one's clearly the hardest, okay? Now note I chose 40 degrees instead of 45 degrees. I think that the publisher who made this problem used 45. So, I don't like that, because then you don't necessarily have to know how to do the trig. All right, so we will note that while we're still here, before I go away, is that our problems are going to be in the RT, so not in the XY, directions. We're going to solve everything in the RT direction. So R being radial, and T being tangential. So it's easiest to see those on this circle. So radial is always out from the center of the circle. So I can go ahead and draw that for all 4 of these locations. And I think it should be clear what I mean by out. I mean out and away from the center. And then the tangential direction will be perpendicular to the radial direction. That's required. It has to be perpendicular. And by convention, we're always going to make that counterclockwise. There's other ways you can do these problems, but I think I'm not going to teach you other ways to do it. We're just going to do it the same way. Okay, and I think, at some other later date, you can learn another way if you like, but it's nice to just kind of go with the standard. All right, so let's go ahead and, no, dadgummit. Okay, so let's see what we can do. We're going to go over here, and we're going to start at the bottom, okay, and rising. Okay, so right at the bottom, I still have that picture over there. So I'll draw a little dot, representing, the biker at the bottom. And let's see here. So let's start with our coordinate systems, right? So we've got R, which is going out, which in this case is down. And then I've got tangential, which needs to go counterclockwise, which means at this particular position, it is going to the right. Now, always remember, if you can't picture which way is counterclockwise, you can put your right hand on the center of the circle with your thumb pointing upwards, and you can just look at which way your fingers will decide is counterclockwise, if you don't want to try to picture a clock face. All right, so once we have those two, now all we need to do is we need to identify the forces. Now, what's nice about this particular problem is the exact same forces at every single location. They just get easier or harder depending on the location. So the 3 forces you're going to have on this particular guy, or this particular cyclist, is you're going to have the force of gravity, which is always going to be down. And I warn you, because when the coordinate systems start turning, people start sometimes kind of confusing which way gravity goes. Just remember, gravity's always down. It doesn't matter what the coordinate system is, gravity's down. All right, so the normal force, okay, so that motorcycle is on a surface. So whenever we have a normal force, it is coming out of the surface and, into or, through or onto the motorcyclist. So we'll have that's going to be going up. And then when there's a friction force, and we know there's a friction force only because we're solving for it, not necessarily because we know what it is or what direction it is. If you don't know what direction something is, I'm going to highly recommend you get into the habit always of just drawing it positive. So in the positive t direction, which is to the right, we're going to write the friction force. Okay, now why positive? So the reason we'll draw it positive is because what's going to happen is you will solve the equations, and if the equations tell you that you got a negative number, you're solving the equations based on which way you drew the arrow. If you solve the equations and you end up getting a negative number for this value, well, that means you drew the arrow in the wrong direction. So for me, it's easiest to draw it positive, and then if I get a negative value, that means that I drew it incorrectly and it is in fact negative. However, if I draw it negative and then I get a negative value, that means it is in fact positive because I did it wrong. That's too confusing for me. I don't like to make that mistake, so we won't do that. All right, so once we're here, you're going to do two things, one right after the other. So you're going to sum forces in the r direction, and you're going to sum forces in the t direction, right? And so they're going to equal mass times acceleration, and then, for each of them, okay? So what I'm going to recommend here, well, there's really no recommendation, just solve them in order. There's no rhyme or reason to this. So let's start with the r direction. On this particular location, the r direction is more difficult because it's got two forces. It's got the normal force and the force of gravity. You want to be a little careful here because you notice the r direction is down. So f of g, which is normally negative because normally y is up. Since r is down, this is in the positive r direction. So we're going to write positive force of gravity. And then the normal force is up, so that's in the negative r direction. So we're going to go minus normal force equals, and then we are just going to recopy the right-hand side over there. Okay, now we'll start expanding. The force of gravity is m times g, and then the normal force will stay the same, and then mar. So this is my favorite part about these problems is that the acceleration in the radial direction is always the same. It is always towards the center. So in this particular case, it's negative, and it's always negative because it's always going the opposite of the r direction. And now we have a choice. We can either write v squared on r, or we can write r omega squared. It's just kind of up to you. It depends on the problem. In this case, we were given v, so we will write v squared on r. Okay, and then we'll draw a little L under that, the storm L, and then we will go ahead and solve this. So if we do this correctly, this is just a bunch of algebra at this point, I'm going to get that the normal force is equal to mg plus mv squared on r. Now, I'm just going to go ahead and I'm like kind of as an aside over here, I'm going to go ahead and calculate these values because they're going to show up over and over and over and over again, right? mg is just the weight, that's the weight of this particular object. And then mv squared on r. This is sometimes called the centrifugal force. It's the thing you think of when you say, oh, the centrifugal force this, or the centrifugal force that. There's no such thing as centrifugal force. Centrifugal force is a fictitious force. It's something that you feel when you are in the rotating reference frame. So like this motorcyclist feels what feels to him like a force upwards on him when he's in that location. However, there is no force upwards on him. It is just that he's accelerating upwards, and so the normal force has to be greater to account for that. Anyway, these two things are going to show up throughout this problem. So I'm going to go ahead and calculate them right now. But please note, okay, there's a weight, and then there's this this quote unquote centrifugal force, which is not really a force. It is just, it's kind of like saying, how much it's like extra force you need to cause you to move in this circular direction. All right, so these two quantities are, well, the weight is 2452.5 newtons, and the quote-unquote centrifugal force is 5041.7 newtons, where we're going to keep 5 sig figs, which is too many, right? Because we're ultimately going to stop at 2 in our final answer. So I usually say keep 2 extra. Anyway, so that's where we are. Okay, so back here for the normal force, we will say the normal force equals the sum of those two. We want 2 sig figs. So when we add them together, we're going to get 7.5 kilonewtons. All right, So that takes care of the normal force. Now let's do the tangential force, and the tangential force on, let's do the friction force, which is in the tangential direction. The only force in the tangential direction is F sub t, and it equals, remember, we leave the right side alone, ma sub t. And now in the next step, we're just gonna, well, we can't really do anything with the force of friction. There's a temptation to expand it into mu times the normal force. But remember, we don't have the mu, and we're not looking for the mu or anything like that. We just want the force of friction. So if we expand it, we don't have it anymore. Okay, so anyway, on the right-hand side, we have ma sub t. The tangential acceleration is 0 because this thing is not speeding up as it goes around. So therefore, the force of friction at position I is 0. Okay, so we know both of those answers, and I'll just kind of, I'll move over here and, put the answers over here on the side. So just so we can kind of keep track. So we'll make a little chart or something. Okay, so now let's go up here and let's look at our motorcyclists at point number 2. Okay, so let's find another spot, maybe over here, and let's go ahead and solve for that. Okay, so here we go. So on the side there, okay, again, remember the first thing we do is draw a dot. That's our motorcyclist, and we will draw, so the radial direction is going out from the center, and the tangential direction will be going counterclockwise. Okay, so again, if you can't picture it, use your right hand and look which way your thumb is going. Okay, so there's the tangential direction. Okay, so now what we're going to do is, let's see, we need to think about our forces. It's the same 3 forces at every location on this whole thing. So let's see, always the gravity is going straight down, so the force of gravity is downwards. Okay, the normal force is always coming out of the surface, okay, and through the motorcyclist in this case, force of normal. And then, or really, I guess, onto the motorcyclist. And then, let's see, so friction is always perpendicular to normal force. In this case, we don't know which direction, so I'm going to go ahead and draw it downwards. Okay, and, but we know that it has to go parallel to the road, right? It's causing this thing, something. All right. So let's see, let's start in we'll just always go in the same order for all of these. Sum of the forces in the R equals MAR. Okay, so let's see here in the R direction. I've only got the normal force. So force of normal equals, we're going to leave that right-hand side alone, MAR. Okay, and then let's see here. So normal force, normal force is in the negative R direction. Notice it's inward when the R direction is outwards. So we'll say negative normal force equals M, and then A sub R, okay? Remember, it's always going to be the same thing. It's negative because we're always turning towards the center of the circle, and then it's going to be V squared on R, right? So again, because I calculated these values earlier, this is going to be, this is really easy to solve. So normal force is M V squared on R, and I already know that value is 5.0 kilonewtons, 5.0 kilonewtons, because we calculated that earlier. Okay, so let's go to the tangential direction. So sum of the forces in the tangential direction equals M times A sub t. Okay, in the tangential direction, I've got 2 forces. They're both in the positive t direction. So I've got the force of friction plus the force of gravity equals M A sub t. Okay, remember, we're going to leave that right-hand side alone until we're ready for it. Okay, now we will expand what needs to be expanded. The force of friction, again, we're not going to expand that because it's what we're looking for. And then we've got the force of gravity, so I'll do plus M times G equals. Okay, now on the right-hand side, I got this M times A sub t. We're going at a constant 11 meters per second around the circle, so there's no tangential acceleration, so I'll write equals 0. So if I we'll do a little storm L there. But I'll, write force of friction equals negative mg. So that negative sign indicates that I drew it in the wrong direction. So I drew it down, and it will in fact be up. So the force of friction here is going to be negative 2.5 kilonewtons. Okay, negative in this case indicating the opposite of the sign that I drew it, slash the opposite, the negative t direction. Okay, so, all right. So let's, fill in our chart, and then let's go up, and maybe we can work on this. Oh, we don't want to move that. Let's move on let's work on this position number 3, and maybe I'll do that right up here. So again, we're going to draw a dot. Okay, we're going to make a note of which way is R and which way is T. R is always out from the center. Okay, and T is always counterclockwise. Okay, so again, if you can't picture which way that is, imagine your clock, right? Or just put your right hand right in the center of the circle with your thumb up and see which way the fingers are telling you it should be. All right, okay, sweet. So let's see what we got here. All right, so we've always got the force of gravity is going down. Okay, the normal force is always coming out of the surface. Okay, so the force of normal is down. And then the force of friction, so again, it's always the same three forces. So the force of friction, we don't know which way it's going to go, so I'm going to go ahead and point it in the positive T direction, okay, which is to the left. Okay, and always remembering that the point there is that if we get a negative sign, it just means we assume the wrong direction. All right, so we're going to do the same things we've done over and over again. So the sum of the forces in the R direction equals MAR. And then the sum of the forces in the T direction equals MAT. Okay, so in the R direction, we've got two forces. They're both in the negative R direction. So I've got negative normal force minus the force of gravity equals MAR. Remember, we leave that right-hand side alone until we're ready for it. Okay, so let's see here. The normal force is negative F sub n minus M times G equals, and always, this is like one of those lovely things because it's always the answer here. It's always negative because it's always towards the center, so it's always in the opposite of the R direction, and it's either V squared on R or it's R omega squared. Usually it's V squared on R. Okay, so once we have done that, we will, we can put the little Stormel underneath it, and now we must think about, well, look, everything's negative, so we'll bring it over the other side. We'll say, so the force normal equals mv squared on r minus mg. Okay, so we know these values, so we can, let's see. So we get a nice 2.6 kilonewtons. Okay, again, I'm doing the rounding off screen. Okay, all right. Let's see. So in the tangential direction, however, we will go ahead and let's see here. Okay, let's see. So force of friction is in the positive T direction. Force of friction equals M times A sub T. Remember, we're going to leave that right-hand side alone until we're ready for it. So then the force of friction equals. Now I have to think about, again, we're not going to expand the force of friction here because if we did that, then we would no longer be able to find the force of friction. Okay, so we got M times AT. A sub T in this case is 0 because we're moving at a constant velocity all the way around the circle. So there you go. So we get that one. Cool. All right, so we'll go ahead and fill in our handy-dandy chart. And let's see. And then we're going to go to this last position, position number 4, which of course is the hardest point of the whole problem. And probably the thing that I like most about this problem, aside from the fact that it shows you kind of rotation and how stuff is working. Okay, so let's go ahead and fill in our handy-dandy chart over here somewhere. And then let's go look at this fourth spot over here. Okay. So at this fourth spot, again, the nice thing is the first parts of this should be fairly easy, right? We're going to draw a little dot. Now, the annoying thing is that R here is not, the radial direction is out. So it is not, to the left or right or up or down. It's just outwards, okay? Now, because of the geometry of it, it is 40 degrees off of vertical. So I don't know if I want to put a little theta there to indicate that. And then the tangential direction, okay, remember we're always going to draw that counterclockwise. So it's going off this way, okay? And it is theta degrees off of horizontal, right? Now, we may not care about that. Like the horizontal and the vertical are less meaningful when you're going around in a circle, but they still matter. And the reason they always matter is that gravity always goes straight down. So here's my force of gravity going straight down. Okay, what else? Let's see, we got a normal force, which is coming out of the surface and going, in this case, straight towards the center. So I'll write F sub n. And then the last thing that we need here is we need the friction force. And again, maybe you don't know which way the friction force is. I can give you a reason why we know, in this case, that this friction force is going to be going in the positive T direction. But if you don't know, we're always going to guess the positive T direction. So I'm going to go ahead and put it here as force of friction. Now, in this case, we know this is correct because this motorcycle is trying to maintain 11 meters per second while going down a hill. So in order to maintain that 11 meters per second while going down a hill, you have to hit the brakes. The brakes means that your tires are going to have to grip the ground and push against you. Okay, so that will be trying to slow you down. All right, so let's go ahead and do our two directions. So we'll do, and if you really understood, forces on an incline, you should be okay here. But we're going to do the sum of the forces in the r direction equals MAR. So let's see here in the r direction. Let's see, the force of friction's in the t direction. The normal force is in the negative r direction, so I'll get negative normal force. And then the force of gravity, okay, so we got to do a little bit of trig here, or a little bit of geometry. There's our angle right there. So we want the component that is in the negative r direction in this case. So it's going to be minus force of gravity, and it looks like that's going to be the adjacent side. So we'll use a cosine of theta equals MAR. And we're going to leave that, again, remember, leave that right-hand side alone until we're ready for it. All right, so let's see here. So we'll start expanding. So negative force normal minus mg cos theta equals m. And remember that a sub r, which is confusing, but at least it's easy mathematically. It's always inwards, so it gets a negative sign. And we do v squared on r for all of these because r omega squared is great, but not useful for this problem. All right, so let's see. We're going to not get to use our same numbers we've been using this whole time. But let's see if we can rearrange this. Well, first, we're going to get rid of all those negatives. Okay, and then we'll go, let's see here. So normal force equals mv squared on r minus mg cos theta. Okay, now in this case, this is nice. I'm going to show the plug and chug step on this particular one because, we're going to need one more thing than we have had in the past. Okay, minus mg. mg is 2452.5 newtons. But now we have to multiply this by the cosine of 40 degrees. Okay, so the normal force equals whatever that is. Looks like about 3.2 kilonewtons. Okay, and then let's see. So I guess all we need to do now is we need to go to the sum of the forces in the tangential direction equals ma sub t. Okay, let's see, in the tangential direction, we got the force of friction, which is going to be, in this case, positive because it's in the positive t direction. The force normal is in the r direction, so no problem. And the force of gravity is in the negative t direction, negative force of gravity. And let's see, we're going to need a sign on that one because it's going to be the opposite side. So it'll be sine of theta equals ma sub t. And this one's a little bit easier for us because, let's see here. It's easier because the right-hand side is 0. So, we're going to do our usual mg sine theta. So the force of friction equals mg sine theta. Okay. So that's going to require, us to do a little plug and chug in the calculator, and we will get the force of friction equals, looks like 1.6 kilonewtons. Okay, so let's go ahead and look at a chart of all of that stuff. All right, so I think the idea here, and the reason that I've arranged these like this, is I just kind of thought it would be cool to think about what these are saying at the end of the day. Okay, so if here's our circle, right, and this is obviously a bad drawing. We've got a couple of locations around here, blah, 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 blah. So we've got a few spots that we care about. And let's talk first about the normal force, right? So the normal force at the bottom is upwards, and it's pretty stout force, right? So it's going up here when it's at the bottom, 7.5 kilonewtons. And then when we get over here, right, it's now going inwards at 5.0 kilonewtons. Right, now it's going down at 2.6. It's getting weaker, 2.6. And then over here, it looks like it's getting stronger again at 3.2. Okay, so what gives? It's strongest on the bottom. Okay, now the reason for this, that it's strongest at the bottom, okay, and weakest at the top, weakest up here. Okay, so the reason for that is just straight up, it's about gravity, right? At all point in time, the acceleration is always towards the center, and it is always v squared on r. So the acceleration is always the same and it's always going inwards, okay? Always going inwards. So at the bottom, in order to create that acceleration, we have to counter gravity, right, which is going this way, right? So we have to create this acceleration and we have to counter gravity. So this is why it's the strongest up here. At the top, the gravity is down, and the gravity is helping this particular force to make this particular acceleration. Okay, so that's the rationale behind why the normal force is changing the way that it does. Okay, so now the frictional force, on the other hand, and I don't get to like find me a good color for this because I've now scribbled all over this. Maybe we'll just erase it all. Okay, let's see. So on this case, on the other hand, we've got our couple little locations around here that we care about. And let's consider the frictional force, okay? So the frictional force is 0 here. It is 0 here, okay? And then on the way up, we notice the frictional force is upwards. So this is the frictional force upwards. And on the way down, the frictional force is backwards, okay? So what gives here? And what gives here is that we are trying to maintain a constant 11 meters per second as we climb. In order to do that, gravity is working against you. So in order to do that, on the way up, you must have a force of friction that is upward. So you're going to hit the gas on the motorcycle in order to climb up, right? But what you're doing is you're countering gravity, which wants to slow you down. So you have to so that friction force is between the wheels and the road, and what it's doing is trying to push you up. Now, when you get to the top, there's a brief moment there where you don't have to accelerate or anything, right? Now, on the way down, you're also maintaining that 11 meters per second. So in order to maintain, gravity wants to speed you up all along here, right? So in order to do that, you must hit the brakes. So on the way up, you're hitting the brakes, which means the force of friction is slowing you down. On the way down, you need to hit the brakes. On the way up, you need to hit the gas, right? And so that means you need to cause your wheels to spin, which was backwards on the track, which causes a force of friction to drive you up the circle. All right, so anyway, that's a 27-minute video. That's plenty long. And hopefully that was awesome. All right, take it easy. I hope you all are taking care of yourselves. Always remember, I love physics, and I know that not all of you love physics as much as I do. But remember to take care of yourself, and that is more important than all the rest of this. Okay, so take it easy. Take care of yourself, physically, emotionally, all that stuff. See y'all next time we have class. Okay, goodbye.